Hi everyone, welcome to my Max Academy. In this video, we'll continue with the chapter 1 real numbers from 10th standard CBSE mathematics, and we will continue with exercise 2.3 problem number 3. Fine. So exercise 1.2, exercise 1.2 page number exercise 1.2 page number 11 in your textbook. Exercise 1.2 in the chapter real numbers, which is the first chapter from 10th standard CBSE maths. So in exercise 1.2 we'll continue with problem number 3. In last video we did till problem 2 and I gave few homeworks also. Now it is third problem in exercise 1.2, which is find the LCM and LCF of the following integers using prime factorization method. Using prime factorization method, we should find the LCM and HCF. So in third, I'll do the first subdivision. So the three numbers given are 12, 15 and 21. So 12, 15 and 21. We need to find the LCM using prime factorization method. So which means each number you have to write it as factors of prime. So 12 can be written as what? 2, 6 are 12, 2, 3, 3, 1. So it can be written as 2 square into 3. Right? Now 15 can be written as 3 into 5. You can write only in terms of prime numbers. So 21 can be written as 3 into 7. 21 can be written as 3 into 7. Now what is the HCF? Right? What is the highest common factor? Highest common factor means a number should be present in all the three. So 2 is here. Is it here? Is it here? No. So we should not take 2. Ignore 3. 3 is here. 3 is here. 3 is here. Now all of this is 3 power 1. This is also 3 power 1. This is also 3 power 1. Now among 3 power 1, 3 power 1, 3 power 1, right? Which has the lowest power? All of them have 3 power 1. So 3 power 1 is the lowest. So which is 3 power 1 into anything else is there? Here it is over. Now 5 is here. It should be in all the three. 5 is not there. So we should not write 7. 7 is in both? No. It is only here. So we should not. So we will just have only 3 power 1. So answer is 3. HCF means only the number that is present in all the three. You should see in that number you have to take the one with the lowest power. You have to take the one with the lowest power. Here everything is 3 power 1, 3 power 1, 3 power 1. So you will take it as 3 power 1 only, which is 3. Now LCM. LCM means we will check the number. One number, 1 by 1. So this is 2 square, which is 2. Is 2 present anywhere? No. But still we will write. Even if it is not in this, we will write. For LCM, even if it is not there, we will write. So which is 2 square. The entire 2 square you will write. Highest power we will write. But here 2 power 2 is present only here. It is not in these two. So we can just write that as it is. Then 3. 3 is 3 power 1, 3 power 1, 3 power. Now in LCM we have to write the highest power. So 3 is present in all the 3. But what is the highest power? 3 power 1, 3 power 1, 3 power 1. Everything has 3 power 1. So 3 power 1. Into, now next number is 5. 5 is present in everything? No. If it is not in everything, then also we should write for LCM. But HCF we should not write. HCF means it should be present in all the three. So LCM, yes, 5 is there. Then 7 also we can write. Now multiply all this. Right? So if you multiply all this, what do we get? 7 5 is 35, 35 into 3 105. 105 into 4 is 420. What is your LCM? LCM is 420 and HCF is 3. Clear? Now you can try similarly in third, second problem and third problem as homework. Both has homework. In third, second and third subdivision. Similarly, you have to find the LCM and HCF. Now fourth one. The fourth problem is when you try this, if you have any doubts, you can WhatsApp me. My number is 9840360777. You can WhatsApp me. I will try to answer as much as possible. Fine. Now, next one is HCF. HCF of 306, 306 and 657. That is equal to 9. HCF of 306 and 657 is 9. What we have to find? To find this, this is given. You have to find this LCM. What is the LCM of 306, 657's LCM we should find. 306 and 657. Now to find LCM using HCF, we know the formula. What is the formula? HCF solution is HCF of 306, 657 into LCM of 306, 657 is equal to 306 into 657. Right? That is our formula. LCM into HCF will be equal to A into B. Here what is A? 306, B is 657. What is our actual formula is what? Actual formula is HCF of A comma B into LCM of A comma B is equal to A into B. Right? So here A is 306, your B is 657. So now what is our HCF? It is given as 9. So 9 into this is LCM. This is what we have to find. So LCM of 306, 657 is equal to 306 into 657. So what is my LCM? So LCM of 306, 657 is equal to 306 into 657 divided by 9. So this 9 will come down. So this will stay here. This 9 will go down. Now if you cancel by 9, this goes in 9 how many times? 3 times, 4 times. Right? Now 34 into 657 we have to do. What is 34 into 657? Let's do that. 657 into 34. Right? So 4 sevens are 28, 2, 20, 22, carry 2, 24, 26. 3 sevens are 21, carry 2, 15, 17, carry 1, 19. So 8, 3, 3, 2, 2. So we'll get it as 2, 2, 3, 3, 8. That is the LCM of 306 and 657. 2, 2, 3, 3, 8. Clear? Fine. So this is how we find the LCM. When HCF is given, you can use this formula to find the LCM if HCF is given. And you know the two numbers A and B. Clear? Now we'll go to the fifth problem. Fifth problem is, the question is, it is similar to your example 5 which we did in our previous video. Question number 5 in exercise 1.2. Question number 5 is, check whether 6 power n can end with digit 0 for any natural number n. Right? Check whether 6 power n can end with digit 0. Can end with digit 0 for any natural number n. For any natural number n. So now how do we do this? So solution is, we have to check whether 6 power n can end with digit 0 for any natural number n, which means if I find 6 square, that is 36. Is it ending with 0? No. Then find 6 cube, that is 216. Does it end with 0? No. Like that, if I keep on doing 6 power 4, 6 power 5, 6 power 6, 6 power 7, if I keep on increasing n, will there be some n where I will get a number ending with 0? That we have to check. Actually, it will not. You cannot find anything that is ending with 0, but we have to prove that 6 power n cannot have or cannot end with 0. That we have to prove. Now, how do we prove this? Right? So that is, we will say, for 6 power n to end with digit 0, for 6 power n to end with digit 0, 6 power n must be divisible by 10. Right? If 6 power n to end with 0, if for 6 power n to end with 0, then 6 power n must be divisible by 10, because any number that is ending with 0 is divisible by 10, which means 6 power n must be divisible by 2 and 5. Anything, if 6 power n must be divisible by 10 means what? 6 power n must be divisible by 2 and 5. If 6 power n must be divisible by 2 and 5 means what? 6 power n should have 2 and 5. 2 and 5 as prime factors. It should have 2 and 5 as 6 power n should have 2 and 5 as prime factors. Which means if I write the prime factorization for 6 power n, it should have 2 and 5. It can have other numbers also, but 2 and 5 must be there. Now what is the prime factorization of 6 power n? 6 power n can be written as what? 6 can be written as 2 into 3 whole power n. 6 can be written as 2 into 3 whole power n. That is what? 2 power n into 3 power n. Right? 6 power n is what? 2 power n into 3 power n. So what we can conclude from here? What we can conclude from here? Which means 6 power n has only 2 and 3 as prime factors. Right? So 6 power n has only 2 and 3 as prime factors. Right? Also, this factorization is unique by fundamental theorem of arithmetic. Right? The theorem that we saw in page number 8, theorem 1.2. As per that theorem, this is unique. You cannot write in any other prime factors. It is only 2 power n into 3 power n, or you can write as 3 power n into 2 power n. Only the order can change, but you cannot write any other number other than 2 and 3 as prime factors. So which means 6 has only 2 and 3 as prime factors, which means 6 power n does not have 5 as prime factor. But what it should have, as per, for this to end with 10, it must be divisible by 2 and 5. For that it should have 2 and 5 as prime factors, but it has only 2 and 3 as prime factors. But so which means 5 is not there. Which means 6 power n does not have 5 as prime factors. Therefore, 6 power n cannot end with digit 0 for any natural number n. For any natural number n, 6 power n cannot end with 0. Okay, so this is the proof for the fifth problem. Fine. Now let's go to the sixth one. So sixth one says, sixth problem is explain why. Explain why they have given some number 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. There are two parts. First part is we have to explain why 7 into 11 into 13 plus 13. This number we have to explain why it is a composite number, why it is not a prime number. We have to show why this is not a prime number. Now for that, what do? We will take 13 as common because 13 is present in both. So this will become 7 into 11. If I take 13 common, this will have only 7 into 11. Plus here I have taken 13 out, so it will be 1. So I will get 13. So, right? If I take 13 common from both, here if I take 13 out, then it will be 7 into 11. Again, if I take 13 out, it will have 1. So if you multiply 13 into 7 into 11 is 13 into 7 into 11. 13 into 1 is 13. We will get back this. Then again 13 into 7 into 11 is 77 plus 1. So you get, this is 7 into 11 into 13 plus 13. Can be written like this. Now that is equal to 13 into 77 plus 1 is 78. 77 plus 1 is 78. So that is equal to now 78. Now again, let's see whether we can express this as product of primes. Now 13 into 78 is not a prime number. So let's express 78 as prime 2. This will go 39 times. 39 goes in 3 13 times. Right? No, 39. Yeah. Then this goes 13. So 13. Then 1. So it will become 2 into 3 into 13. 78 can be written as 2 into 3 into 13. So this becomes 2 into 3 into 13 into 13 is 13 square. Therefore, now it is what? Product of primes. So 7 into 11 into 13 plus 13 is product of primes. What are the primes? Product of primes 2 into 3 into 13 square. Product of primes 2 into 3 into 13 square. Therefore, 7 into 11 into 13 plus 13 is a composite number. Composite number. It is not a prime number, because if a number is written as product of primes, then that number is a composite number. So we have written this given number as a product of primes. Therefore, this given number 7 into 11 into 13 plus 13, this number is a composite number. That is the proof. So we have proved that the given number this is the composite number. Clear? So we will do the second part of that. Sixth has the second part. So the first part I did. Yes. So the second part for the sixth problem is sixth, second one. That is, we have to show again 7 into 6 into 5 into 4 into 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. We have to show that it's a we have to explain why this is a composite number. Now what do we do again here? What is common here? 5 is common. If I take 5 common, I'll have 7 into 6 into, this is 4, because I have taken out 5. So 7 into 6 into 4 into 3 into 2 into 1 plus 1, because I have taken 5 common. 5 is taken out of common from this whole thing is one term. This whole thing is one term. From here I took 5 common. I will write the rest 7 into 6 into 4 into 3 into 2 into 1 plus 5. 5 is taken out from here, then it will become plus 1. Right? So that is equal to 5 into, now multiply all this. 7 into 6 into 4 into 3 into 2 is how much? Let's do that. 7 6 are 42. 12 2s are 24. What is 42 into 20? 24 2s are 48. Carry 4. 24 4s are 96. 100. Right? Right? 24 2s are 48. Carry 4. 24 4s are 96 or 92. 96 plus 4 is 100. Right? The 6 into 6. 36 9. Yeah. So 1008. 1008. This is plus 1. So which is 5 into 1009. 5 into 1009. I guess 1009 is a prime number. 5 into 1009. So we have written it as, so now the given number 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is equal to 5 into this. So which means it is written as product of primes. Product of primes, that is 5 into 1009. Both are prime. I think 1009 is also prime. Right? So therefore it is written as product of prime. Therefore it is a composite number. It is a composite number. Which is a composite number? This given number. This entire thing is one number. The entire thing is a composite number. Clear? Fine. Now let's go to the seventh problem in exercise 1.2. Right, so seventh problem in exercise 1.2. So what it says is there is a circular path around a sports field. There is a circular path. Suppose there is a circular path. A circular path like this. Fine. There's a circular path like this. Fine. And Sonia takes 18 minutes to drive one round of the field. And Ravi takes 12 minutes for the same. Which means to go one round this circular field, Sonia takes 18 minutes. And Ravi to go around this, he takes 12 minutes. Now suppose both start at the same point. Suppose both are starting here. Ravi and Sonia. Ravi and Sonia. R and S. Ravi and Sonia are starting at the same point here. Both are starting here. And both start at the same point and at the same time, and they go in the same direction. They both start at the same point and at the same time both are going in the same direction. Which means both are going like this. Both are going like this. This is the direction they are going. They are going around the circular path. After how many minutes will they meet again at the starting point? After how many minutes they will again meet at the same point here? First they start, both of them start from the same point here. At the same time, both are starting and going like this. But to go one complete round, Sonia takes 18 minutes, Ravi takes 12 minutes, which means Ravi goes faster than Sonia, right? Fine, so Ravi goes faster than Sonia. So Ravi takes 12 minutes to complete one circle, Sonia takes 18 minutes. Now after how many minutes, both of them will meet at the same point they started. See, for example, Ravi is going faster. Suppose in 12 minutes, Ravi will come back here again. But Sonia will be somewhere here. At 12th minute, because Sonia takes 18 minutes, only 18 minutes she will come here. Ravi goes, Ravi and Sonia both start from here. Both are going, and Ravi takes only 12 minutes to come back to this point. But Sonia takes 18 minutes to come back. So in the first round, after the completion of first round, Ravi will be here, but Sonia will be here. So both will not be at the same point. Again, when Ravi moves somewhere, Sonia will come here. And 18th minutes, Sonia will be here, but Ravi will be somewhere here. He will be in the next second round. When Sonia completes the first round here, she will come back here after 18th minute or after 18 minutes she will be here. But Ravi will be somewhere here. Again, in 24th minute, Ravi will come back here again for the second time, but Sonia will be somewhere here. So after how many minutes, both of them will be at the same time, which means we need to find the number, right, which is the lowest common multiple, which means we should find the LCM between the two numbers, which are 18 and 12. Sonia takes 18 minutes, Ravi takes 12 minutes, right? For them to meet at the same point, both of them should complete the circle. Both of them should complete the circle at the same point, right? Which means you need to find the lowest common multiple between 18 and 12. Say for example, if we try to think logically, see, 18th minute, Ravi, this is Sonia. So round. First round he will complete in 12 minutes. She will take 18 minutes. Right? Second round, Ravi will complete in first round, he will complete in 12 minutes. Second round, he will complete it in second round. Round 2, he will complete in 24 minutes. Another 12 minutes. She will take 36 minutes to complete the second round. Now round 3 for Ravi will be 36. But Sonia's round 2 is what? Also 36. Which means after Sonia completes 2 rounds at the same time, which means 36 minutes, Sonia will complete 2 rounds, but Ravi will complete 3 rounds, which means both of them will be at the same point. When? After 36 minutes. Because 36 is the number that divides both. And 36 is the lowest common multiple of both 12 and 18. So by the time Sonia completes the second round, Ravi would have completed the third round, and both of them will be the same point. Both of them will come back to the same point, but the only thing is Ravi would have completed 3 rounds, Sonia would have completed only 2 rounds. Both of them will come at the same point. But that happens after how many minutes? 36 minutes. If both of them should meet at the same point, means both of them will be at the same point here. But Ravi would have completed 3 rounds in 36 minutes, but Sonia would have completed only 2 rounds. But ultimately, we are not worried about whether they are completing same number of rounds. Whether they are meeting at the same point after how many minutes? They will meet at the same point after 36 minutes. So the solution for this is, right? So to find after how many minutes both Sonia and Ravi will meet at the same point. Both Sonia and Ravi will meet at the same starting point. We need to find the LCM of 18 and 12. We have to find the LCM of 18 and 12. So now, how do we find the LCM of 18 and 12 using our prime factorization? I'll go here. Right, LCM, which means 18 can be written as 2 into 3 square. 12 can be written as 2 square into 3. Right? Now, how do you find LCM? LCM means we will check if a number is present in both, we will take the highest power. So 2 is here, 2 here also I have 2, here also I have 2 power 2. Here it is 2 power 1, which is highest power, 2 power 2. So I should write here. Then again 3 is present in both. If it is present in both, we have to take the highest power. This is 3 power 2, this is 3. So highest power is 3 power 2, 3 power 2. So 3 power 2, 2 power 2 into 3 power 2 is 4 times 9, which is 36. So therefore, we should say after 36 minutes, Sonia and Ravi will meet again at the same starting point. Clear? So this is how we do. Fine. So the answer is 36 minutes. Clear, everyone? Fine. So I will end the class here, session here, and you can watch my next video for the continuation of this chapter. Thank you again. Thank you. See you in the next video.